Okay, guys, we'll wrap it up this time. Thanks for sticking with me. I know this hasn't been the most exciting thing in the world, but we really, by the time we're done with this video, should have finished about 2.5 days of content. It's just going to buy us a lot of time to practice calculations together and really just make you mean machines at this kind of stuff. Like I said, sorry they were boring. I'll try to think of a way to make the next couple more exciting when we find another piece of content that this works for real well. I don't know what I'll do there. Maybe I'll have to dress up in the mole costume or something. You know what, on second thought, that would be super creepy. Let's not even worry about that. Let's go ahead and just move on from here. So we've been finding the deviation, right? Which I guess I didn't explicitly say it, but the deviation is how far the measurements vary from each other, right? So your average deviation would be how far on average each measurement deviates from each other, or the mean, right? You can also, in some cases, it's more useful to find the percent average deviation, right? Now the percent average deviation is going to be relative to the size of the measurements. So it's sometimes a more convenient factor. It kind of gives you a more realistic look at how far the deviation really is in the cases where you have a very large or very small value. Percent average deviation is very similar. We're just going to take our average deviation that we found in our above step. Okay, we're going to divide it by the mean, our average, right? Multiply by 100, and then you express the answer in the same way. You'd write your mean plus or minus your percent deviation. Now, your percent deviation is always expressed to only a single sig fig. I'd love to be able to explain to you why that is, but honestly, I couldn't tell you. It's just always been that way. It just kind of is the standard. One of these days when I have free time, I'll go try to figure out where that came from, but it's just always kind of done that way. Okay? Now we have one last type of deviation. Let's move on. Standard deviation is the one you guys have probably heard about. Okay? Standard deviation has the same steps as before. Let me show you. We're going to go through and find the mean. Then we're going to subtract each value from the mean to find their absolute value, their absolute deviation. We take each one of those and square them. Then we sum them all together. That's what this crazy little sideways E symbol means. That means you sum all those values together, the square of all those values. Okay? Then we're going to divide by the number of data points you had, minus 1. That's what n would be. So for our previous example, we had 4 data points, right? So here it would be divide by 3. And then finally, you're going to take the square root of all of that. So I know it's not very clear in the PowerPoint here, but this square root should be over everything here, not just the numerator, okay? So our sum up here is just going to be basically that variation for each one of those individual measurements, squared, summed together, okay, and then divided by the number of data points minus 1. Standard deviation is, it's a really good way of basically tracking down random error. Remember when we were talking about different sources of error before, and I said that random error had many different sources? You can't really identify it or control it very well. If you have a scale that's consistently measuring high, you can identify that, and it's done. You can fix it. Random error, you really can't do that with. So instead we calculate standard deviations, and that will allow us to see if we have a source of random error that is affecting our values. Okay? It's typically used on large sets of repeated data. I mean, it doesn't make much sense to run a standard deviation on something you only did once. For instance, a lot of times during exams, I'll run a standard deviation just to see how far apart the scores are spread. That'll tell me whether I have a lot of kind of outliers, really high or really low scores. You guys probably haven't seen this a lot before. You'll see it a lot referenced in college. You may have seen it in a couple of classes. But like for instance, grades are always whoa, that was horrible. Sorry, hard to draw with a mouse. Grades are typically in what we call a bell curve form. Again, if you haven't heard of this before, we can talk about it in class if you guys have questions. But in an ideal world, the grades in a class should be in a bell curve. Your average, most of your students, around your 70 here, should be in the bell curve. So most of your kids should score right here at your average, 70 by definition, right? You should always have a couple of outliers here where you have a couple people who flunk and then a couple people who just ace it, okay? That's kind of where the whole idea of average is going to come from. That's what standard deviation is based around, okay? how much each one kind of deviates. The good news is, because in a perfect world with a bell curve there, one standard deviation is actually a unit. All values that fall within a single standard deviation should, in a perfect world, be about 68% of your measurements should fall within a single standard. Okay, and then within 2 standard deviations, you should find about 96% of your measurements. So it's a really good indicator of basically how far apart these things are spread. How closely the measurements were kind of an indicator of precision. And again, really it's used to track down random sources of error. Well, I shouldn't really say track down. Identify random. Indicate that there is a random source of error. You're going to have to use your brain to actually identify what that random source may be. Hopefully I didn't just totally confuse you there. All right, nota bene again. Got a couple things to throw in here. First one I've already written on the PowerPoint there. The value of the mean, by the way, okay, is going to be based on the precision, not the sig figs. In most cases it's the same thing, but what I mean there is it should be based on the number of decimals typically, not the actual sig figs. Okay? The precision for the mean and the deviation should always match, with the exception, of course, of the percent, because it's going to be based on the overall size of the value itself. A couple other small things I should throw in here for you. Let me turn the pin on here. A couple of symbols you may see in passing that I kind of want to show you. This symbol right here, all right, kind of like an upside down hat there, is often used as a symbol for standard deviation. A lot of times you'll also people write mean or average like this. Okay, that's the symbol average with a little line over the top. All right, before we move on to kind of our next little topic, let's finish up this whole data discussion, right? Let's clarify, now that you actually know what some of these things are, let's talk about when they're useful and what you use them for, just briefly. Okay, sig figs are pretty much always the go-to. They're the easy way out. Everything you do with sig figs. You guys know that. That was like one of the big things from Chem 1, right? These other things we talked about are for more specific circumstances. Propagated error can be used in pretty much any experiment, okay? And it's a really good habit to get into. Again, you're not required to unless I ask you, or unless it's one of those labs that I'm going to be collecting for internal assessment, but it can be used on pretty much anything. Now, these statistical methods that we covered here at the end, all these deviations, those are primarily for experiments when you have multiple data sets, like maybe we collected data from the whole class, or maybe you did the experiment over and over again, or in some cases for an entire population. It's for large data sets where you need to find the deviation from that standard of all these multitude of measurements. Okay? So average deviation is kind of your starting point. From that you always get your percent deviation. And then standard deviation then is going to be the one that we're going to use to basically identify whether we have a random error that we need to try to identify or contend with. Okay? Hopefully that helps you a little bit. Again, if you have any questions, make sure to make yourself a little note so we can talk about them in class, okay? All right, so the last thing I want you to do is a little practice problem. Because of the fact I'm writing with a mouse, I'm not even going to try to write out the answer because it would be completely illegible. I want you to go ahead and try this on your own, using your notes and whatever time you need. Bring it to class with you next time I see you, and we're going to go through and check your answers in partners and then together as a group. So bring it with you so I can see you actually listened to the video and you tried it. Here is your example problem. Okay, you got 7 groups of students, each experimentally determining a thickness of a zinc layer. That sounds strangely familiar. On a piece of galvanized iron. The values are going to be reported here in centimeters. Okay, and you're going to find for me the mean value of the thickness of the zinc. I need an average deviation, a percent deviation, and a standard deviation. That way we can go through and kind of compare them and see what the implications of all of those will be. So go ahead and try to solve that one on your own. Bring your work with you to class next time I see you. Okay guys, thanks for sticking with me. I'll see you soon.